Boom. Hello and welcome back to Calculus 1, section 2.6, continuity. So let's take a look at what it means for a function to be continuous and use it for various other concepts that are coming up. In general, people like to think about continuity of function as just one stroke, right? That it's uninterrupted. And if you are able to draw a function without lifting the pen or interrupting the motion, it would say it's continuous. And if you have to kind of stop and jump to a different location, in that case, the function would not be continuous. Now that is some kind of a visual, right? Some kind of a visual representation of what's happening, but we can do much better than that. There are functions in calculus that are continuous, and you have to draw those segment by segment. And those functions are studied in advanced calculus and so on. So, yeah, this is nice and cute and it works, but it's not everything to the story. If we want to study continuity, we have to first study continuity at the point. And then we look in the neighborhood of the point, extend it to the entire function, and then we have some rules and regulations moving on. So before we do anything, we have to define continuity at the point x equals a. So continuity at the point. Function f of x is continuous at x equals a, at a point x equals a if, and now we have three conditions, they all have to hold. First condition is f of a exists. Second condition, limit of f of x as x goes to a exists. And the third rule, limit of f of x as x goes to a is equal to f of a. So technically saying 1 equals to 2. This is your continuity at the point. So function f of x is continuous at a point x equals a if these three conditions hold. You must learn these. Otherwise, meaning if any of these fails, f of x is discontinuous. At x equals a. So this is the full definition of continuity at the point. And now we can check this. Well, let's do with something very easy. Say your function f of x is x squared plus 3, and you want to check the continuity at x equals to 5? Well, rule number 1 says that f of 5 must exist. Well, great. That's just 25 plus, let's do 5 squared plus 3. So this is the pre-calculus part, which gives us 28. I use the green check because it passed. Can I find better, darker green? So pass on that one. Number 2, limit of x squared plus 3 as x goes to 5 must exist. Well, this is one of the functions that without zeros in denominator or anything weird happening. So yeah, I have 25. You can just plug in, right? Nothing weird is happening. You get 28. So that exists and that passes. Rule 3 says that the 1 needs to be equal to 2. Well, 28 is equal to 28. Therefore, that passes as well. So now, since all 3 passed, function is continuous. So, since all 3 parts passed, f of x equals x squared plus 3 is continuous at x equals to 5. Is it continuous at x equals to 3? Yeah, we gotta do everything from scratch now. Is it continuous at x equals to negative 10? Yeah, but we have to do everything from scratch, right? This tells you the continuity at the single point. It doesn't tell you anything about the entire function. It's just this one point, there is continuity there because it passed these 3 rules for that point. How many points are there for x squared plus 3? Infinitely many, right? All right, let's get busy. So now there are 3 rules, so there have to be 3 ways to ruin continuity. And we achieve that by, let's consider these three different pictures. So the first graph, let's say, is the one that you have seen earlier. Then let's say you have this graph. And finally this graph. So let's consider these 3 graphs. It shouldn't take mental power here to see that all 3 are discontinuous, right? There is a jump on the first one, and there is the open circle in the second and the third. So they're definitely all discontinuous. What I'm wondering is which rule out of 3 rules is the one that it's violated in these cases. So let's go with the first picture. Which rule is violated? Rule 1, Rule 2, Rule 3? Well, let's go with the Rule 1. Rule 1 says function value at a has to exist. Do we have f of a in the first picture? Yes. Where is it? Where is it? Where is the f of a? It's the bottom, the black dot, right? So it passed the first case. Perfect. Number 2, limit x goes to a of f of x. Does that one exist? No matter what you say, I'm going to keep my poker face until you tell me exactly why you say yes or no. Does it pass the second one? Does the limit exist?
No.
I'm not changing my face. Until you tell me why.
No, because the black dot's not part of the function.
It is.
It's not connected.
Oh, it's not connected here?
It doesn't pass through it. No, they don't approach
You-
the black dot.
Thank you. Using the theorem. Theorem says that the left approach and the right approach, right, when you approach the limit from the left and approach the limit from the right, the y value has to be on the same height, and it's not in this case. So the second one fails, therefore we're not even going to check for the third one, because, right, as soon as you run into one that checks out, the whole problem is gone. Great. Next picture. Does it pass the first rule?
Yes.
Yes, we do have f of a. F of a is the black dot that it's in the middle of the picture. Great. Do we have the limit for rule 2? Limit of f of x as x goes to a. Yes, why? Yes or no? You said yes. I'm asking why. What is the limit? Again, you should be using the theorem. Limit from the left and limit from the right, do they meet at the same wide height? What do you mean no? The limit from the left goes to the open circle as the function goes into the open circle, and the limit from the right goes into open circle, so both agree that the limit L is there. So it does exist. And it's L. It's whatever the open circle is. How about the 3? Is the y value for the open circle and the y value for the closed circle the same? No. So that's where it fails. So function value exists. That's what the black circle is. The limit exists. That's what the open circle is. But they're not at the same position, right? The same y elevation. So the third one doesn't fit. And finally, the third picture. How about rule? Do we have function value f of a? Do we? No. There's no black circle anywhere. If you try to compute this by bouncing off of the function into y value, when you go from a, it's just going to shoot straight through the hole and go up, and never bounce into the function, into the y. So it fails. Function value doesn't exist. So now you see the 3 rules, and you see that if you violate any of the 3 rules, the function becomes discontinuous immediately. So you can violate rule number 1, rule number 2, rule number 3, in any one of these. There are further divisions of this in terms of the removable discontinuities and non-removable discontinuities, which, I mean, you can think of it as, you know, when you have this discontinuity here as let's say a 100-foot cliff, you can't fix that, all right? You can build an elevator, and that's technically what you can do. But there is no way of continuity in terms of a road, right? If you're not going to tunnel through the rest of the planet. Now, this part over here would be called something that's a removable discontinuity, and you can think of a bridge that it's missing a section, and then there is a section somewhere else that you can plug in eventually and make it continuous, because I hope you all like to drive over continuous bridges. And this one is another one of non-removable ones, because if you think of this as a bridge, and then a section of the bridge is missing, let's say in the middle, over here you have something to plug in and fix it, and over here nothing that exists or can be produced can be plugged in to fix. So there are further divisions. Everything that we do in this class can be eventually extended to more these divisions and so on. So what do we know so far? We know that the function is continuous at the point if it satisfies all three rules, and if it fails on either one of the three rules, it's discontinuous at that point. And these were the ways in which you can have a discontinuous function. Discontinuities could be these jumps, like for a piecewise functions, for step functions, like your tax, right? Taxes, that's a step function. It's a discontinuous function. You don't go gradually increasing the percent. It's a jump of from 15 to 25% at certain amount, dollar amount, and that's it. So you either made more than that, or you didn't. The trick is, right, to know where you stand so that you can maybe donate some money so you can bring back that into the lower tax bracket, if it's close to. And now you have the notion of vertical asymptote as well. That's a discontinuity. You have to lift the pen and start drawing, continue drawing the function on the other side of the asymptote, because you can't pierce through vertical asymptote, and that's that. Good. All right, time for global continuity. So, function is globally continuous if it's continuous at every point. I'm just trying to find all these definitions, and I don't see them. All right, so I can't find it, doesn't matter. So function f of x is globally continuous if it is continuous at every point in its domain. Now you immediately see an issue here, right? If I'm asking you to find the global continuity, and that's, right, infinitely many points, now you have to sit down and check all of the infinitely many points, which is a little bit not practical, right? Because eventually you want to go and sleep. To help with this statement, we have a theorem which states these functions are globally continuous on their domains, and then a whole list of functions, so you don't have to check every point. So let's have blue. Another theorem which states following functions are globally continuous on the entire domain. Polynomials. This includes constant, linear, quadratic, cubic, whatever you can come up with. All polynomials are globally continuous on the entire domain. Exponential functions. Logarithmic functions. Radical function, square root of x. Sine x and cosine x. Vertical asymptote at pi over 2, 3 pi over 2, right? Infinitely many vertical asymptotes, therefore infinitely many discontinuities. So polynomials, exponential, logarithmic, radical, sine x and cosine x, that's just 2 out of 6, are continuous everywhere. If you want to add inverse tangent, you can. Inverse tangent is globally continuous everywhere. Here, let's add inverse tangent, because it's going to pop up eventually. And we're just going to leave it here, because we can make this into more. So let's find another color. I'm really having fun with it. Even more colors. Yeah, way too much. Less colors. What's a good color for the next theorem? Alright, fine. Purple. The next theorem states that all combinations of continuous functions are continuous, including function composition. So, all combinations of continuous functions are continuous, including function composition. Now this means that if you have two continuous functions f and g, so now I'm just going to state as a theorem, or if f of x and g of x are continuous, then f plus g, f minus g, f times g, f divided by g, provided that g is not 0, f squared, and finally f of g of x and g of f of x are all continuous. So this is what we have as a second theorem. So now, is x cubed minus 7 continuous globally? X cubed minus 7. Is it continuous globally?
Yes.
Why? X cubed. It's not exponential, it's the other one. X cubed. But that's the right attitude to have. What's x cubed plus or minus 7, whatever I said? What type of function? What is this? Polynomial. So, is it continuous? Yes. It is continuous because x cubed minus 7 is a polynomial. And if it's a polynomial, by the theorem we have up there, the blue one, it's globally continuous on the entire domain. Domain of polynomials is negative infinity to positive infinity. So there we go. Now move to some spicier examples. Say is y equals x cubed minus 7 over x squared plus 1 globally continuous? Oh, hello, writing paragraphs. So this problem has no calculations to it. To answer this calculus question, you have to write a paragraph. So let's do it. Answer. X cubed minus 7 and x squared plus 1 are polynomials. Therefore, continuous on negative infinity to infinity. That's the domain for all of these. Now, we have an issue. X squared plus 1 is the denominator, and that's 0. It's going to include the vertical asymptote, which includes discontinuity, which creates problems, right? So now, since x squared plus 1 equal to 0 has no solution, denominator will not produce discontinuities. Again, it's never 0. We know it's bad when it's 0 because vertical asymptote happens, and as soon as the vertical asymptote happens, you have discontinuity. So again, x squared plus 1 can never be 0, and because it can never be 0, you will never be dividing by 0, therefore no vertical asymptotes, open circles, or anything like that. So denominator is not producing any discontinuities. We can say quotient of two continuous functions is continuous provided that the denominator is never 0. In our case, denominator cannot be 0. Therefore, y equals x cubed minus 7 over x squared plus 1 is continuous, globally continuous, whatever. Yay! An essay in Calc1. Get used to it. I mean, majority of you are in business and, right, so you love this kind of stuff anyway, so you like writing and reading, right? Otherwise you'll take physics, which is also writing and reading, let's see. Is it time to jump to the next course? Sure. Now, I just started using the new app, so I'm just gonna go back. Calc2 F17, and those of you going to Calc2, let's take a look at integral test. Integral test, there we go. Now look what integral test says. That's the definition that you have to learn in Calc 2. It says if f of x is continuous, positive, and decreasing, then you do the stuff down there. What does it say on the first line? Continuous, right? So what do you have to do before you start this Calculus 2 problem? You have to do the paragraph we just did. So if I have an example, like this one, you have some kind of series, you create the f of x, which you see just to replace the k with x, looks the same. Question number 1, is it continuous? Okay, x plus 10 is a polynomial, therefore continuous. Cube root of x is rational, therefore continuous. All on the list we learned today. Function composition of two continuous functions is continuous. That's also our theorem. That one was purple. Since the square root cannot be equal to 0, because our domain was from 1 to infinity, the entire function is continuous. Your problem today that you are learning as the entire problem is this first blurb, followed by second blurb, third blurb, and then finally in purple you can do the problem. Yeah, welcome to Calc 2. So don't get the attitude that you're learning stuff in this class just to pass the first exam, because this stuff is also going to be on the final. It's going to be used in chapter 4. And yay, we have Calc 2, differential equations, and other courses coming up which all use these concepts as you move on. So now you see the placement of these little essays. Keep it down to 4 or 5 sentences. I don't need a 30-page research paper on if function is continuous, if it contains, 2 or 3 functions in there. It's good enough to, quickly write just the points that are needed. So you establish your, you show your knowledge that you know these are polynomial functions. The theorem stated they're all globally continuous. Great. And then combinations or the function composition of these guys is going to be also globally continuous. And that's that part. So, okay, let's take a look at another example of this. And then you can practice one example. So say y equals e to the sine x. I'm going to play with this function in chapter 3 a lot, so why not talk about it now in terms of continuity? All right, so where do I start? The question is this continuous, right? Well, I start by stating that both e to the x and sine x are globally continuous. This statement is your theorem in a light blue. Here is your e to the x, and here is your sine x. So you have to learn that theorem, the list of all continuous functions. Right, the list. So the first sentence established each of the functions. Now you see that the next sentence is going to be the one that says that function composition of two continuous functions is continuous. And you're done. Function composition of two continuous functions is continuous. And you're done. Remember when we did decomposing of the functions on the first day? It's needed for this class. So what do you have? You have your f of x is equal to e to the x, and your g of x is equal to sine x. And now if you want to find f of g of x, you will replace every x of f with g. Replace every f of x, every x of f with g. So e to the sine x. You decompose this in your head, and you get e to the x, continuous function, sine x, continuous function, and then you have the function composition to come up with e to the sine x. And the theorem, the purple theorem this time, said that function composition of continuous functions is continuous. That was a two-sentence problem because it was really cheap. We did not have to worry about denominator and checking for zero and so on. This is just a reminder of function decomposition and so on. How's the stream doing? So it's alive. Okay. All right, good. Let's pick something from the book for you to enjoy. Oh, by the way, before I just ran into this, we are going to talk about this soon, but this theorem, the way they have, is just terrible. So we have to talk about the details. Essentially, I want you to just cross this out, completely cross it out, and just use what I gave you, and I'll explain the details once you solve the problem for practice, to practice the essay a little bit. So let's say the f of x is given as x cubed, 5x cubed times the 4th root of ln x. So try this for a little bit. You can talk to people sitting next to you, it's okay. Unless you can't stand them, obviously, then don't. All right, let's establish this. So first of all, number 5 is not going to contribute positively or negatively to continuity. We don't have to worry about number 5. We are going to state first that x cubed and 4th root of x and ln x are all globally continuous. So the first one is a polynomial, second one is the radical function, and the third one is logarithmic function. They're all on our list. And that's the blue list we have. Now, we have to create this piece here using function composition. So we say that function composition of two continuous functions is continuous. Therefore, 4th root of ln x is continuous. So now we have that. And finally, multiplication of two continuous functions is continuous. So 5x cubed times the 4th root of ln x is continuous on the entire domain. And that's the essay. You don't have to double space it. Okay? Yeah, 3 or 4 sentences. If you have function compositions, you have to establish those parts first, and then you go with addition, subtraction, multiplication of functions. If you have a division, you have to make sure that the denominator is not 0. Every time the denominator is allowed to be 0, you guys have discontinuity. So that's that part. Tangent function has infinitely many discontinuities because tangent function has infinitely many vertical asymptotes. So you have to be careful about those things. Also, the other 3, secant, cosecant, and cotangent, are also globally discontinuous because they have infinitely many vertical asymptotes. Let me point that out. Tangent x is sine x over cosine x. Cosine x is equal to 0 at every x being pi over 2 plus pi and pi. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Every single half pi over 2 plus something like that is going to be a vertical asymptote. Because cosine is 0 and cosine is in the denominator. So we see that the tangent has infinitely many discontinuities. Now the textbook says that tangent x is continuous on its domain. What they fail to realize and recognize in the book is that the tangent is continuous on the restricted domain. And that is something that we have to work on right now. We talked about the restricted domain to make functions, trig functions, friendly enough to have inverse functions for those. So we know that sines and cosines are infinite waves, and they are globally continuous. They are on our list, right? I'll call it a blue list. So we're good. Now the other 4 are not continuous. But we have a concept that we call piecewise continuous, which means, sure, there is going to be discontinuity somewhere, so function is not globally continuous, but there are these intervals on which the function is continuous. And sometimes we need to focus only on those. So let me go and state y equal 1 over x, okay? I have a graph which you guys seen 5,000 times so far. And we all are immediately going to agree that this function is discontinuous at x equals 0 because there is a big fat vertical asymptote right there. Right? So immediately we say globally discontinuous because vertical asymptote at x equals 0. And that's the end of the story. This is globally discontinuous, and that's that. But one over x is continuous on parts of the domain. And sometimes that's all you need for your application. So negative infinity to 0 is perfectly continuous, and also 0 to infinity. So we have to be clear. 1 over x is discontinuous globally because there is an asymptote at x equals 0. However, if you consider 0 to infinity, well, that's this continuous piece over here. And you go from 0 to infinity, that piece is continuous everywhere. Now, a little, again, going back to Calculus 2 and talking about this. Is this exploded? No. Talking about this, I'm going back to this problem over here where I have 1 over n and I create 1 over x, but it's on the domain 1 to infinity. Because the sum over there was 1 to infinity, the domain I'm considering over there is 1 to infinity. You see? Continuous. And I have the graph for 1 over x, and look at my red line. It starts at x equals 1 and goes to infinity. Yeah, 1 over x is discontinuous at 0, but that 0 was not included in my interval at all. I only consider 1 to infinity, and that's continuous. So moving on to next courses and everything else, you guys have the this notion as well. So you can take the part of the entire domain and just focus on that part if that is it that solves the problem. So I'm able to continue with the problem and eventually do whatever I need to do for Calc 2 to solve it. So in that light, when I'm looking at this, maybe I don't need global continuity all the time. Maybe I just need the part of it. So this function is piecewise continuous. There are two pieces that are continuous, and still globally this function is discontinuous. And that's that. The last concept in the book, like 2 minutes here, is the intermediate value theorem, which we technically don't use. I think you have a problem on the lab. I'm going to explain this. So, intermediate value theorem. And the statement goes like this. Suppose f of x is continuous on interval a to b, and L is a number strictly between f of A and f of B, then there exists at least one number C in AB satisfying f of C equals L. It doesn't sound like much. It is extremely important concept-wise, but we don't use it for calculations because it's pain in the neck. So these words make a lot of sense when you see the graph. So you have your A, which produces f of A, which is the y value. And you have your B, which produces f of B. Again, y value. Now they say there exists L. Let's say right here, which is in between f of A and f of B. So now they say there exists at least one number C that makes that L. Well, you can find that C, look. There it is. Now you might say, what's the big deal? Well, when you look at it this way, it brings order to things, but yeah, not a big deal until you shift this graph down. And when you do that, you run into a problem that looks like this. And this point here is a solution to the equation. So now look what you have. This is going to be your C. And if you pick your, let's say, A over here, and your B over here, note that your f of A is negative and your f of B is positive. This situation traps the root of the function, the solution to the equation. And depending on how much time you have, you can calculate the solution to any equation by computing numbers. But it's really labor intensive. So instead of me going for 10 hours over here to compute an example, I'm just going to jump to my other calculus class where I did this so that you can see the procedure. You have something similar on your lab to find the intervals which contain the solution. Now I'm just going to jump into my Calculus1 over here somewhere for Saturday. Okay. Oh, that's the one. And if I go here at the end of the lecture, here is me computing this thing. What I wanted to do is I wanted to find the answer for equation x squared equals to 3. Now we know that the answer for that is plus minus root 3. Root 3 is about 1.73, and you're done with that, right? But say you don't know any of that stuff, or imagine whatever other equation that you don't know answer to. What you do is you make a guess on the interval. You say, my answer, I hope there is a solution. I hope that the answer for this equation is on interval 0 to 5. So that's just your guess. Then you compute function value at 0 and function value at 5. And what you get is that 1 is less than 0 and 1 is more than 0. Yay. That traps the solution, you know, to be between 0 and 5. Now we know it's already 1.73, so it's definitely between 0 and 5. But this thing over here proves that there is a solution to the equation between 0 and 5. So what do you do next? You make a next guess. You cut the interval into a smaller interval. And what we chose is 0 to 3. So now compute at 0 and 3, and you get less than and larger than again. That means that one side is below x-axis, one side is above x-axis. When they connect them with the line cuts through x-axis somewhere. That is the root, that is the answer, that cut, wherever it happens. So you are trying to locate that cut. Okay, great, so now you are not longer on 0, 5, now you're 0, 3. Make another guess. 0 to 2. Great, again, less than, larger than. The solution is still in that interval because, right? Make the next guess, 0 to 1. Okay, here is the trouble. When you compute 0 and 1, they both came out to be less and less. So that means that the root is no longer in that range. Well, if the root is in between 0 and 2, and it's not between 0 and 1, then it must be between 1 and 2. Again, we know the root is 0.73. All right, fine. So now we are at the interval 1 to 2. I don't need to check 1 and 2 because logically, right, if we know the root is from 0 to 2 and it's not in 0 to 1, it must be in 1 to 2. So now cut that interval in half. We did 1.5 to 2. We got 1 to be less than, 1 to be larger than. Again, what is this less than and larger than? Guys, when the function cuts through x-axis, when you pick value a, in this case, it's negative, and you pick value b, it's positive. See that? So that's what it means. The y value is less than 0, y value is more than 0. So we get both of these values to be 1 less than, 1 more than. Then we pick 1.5 to 1.8 again. And then finally 1.7 to 1.8. We pin down the first decimal of the answer. We know that the answer is starting with 1.7 because all of the numbers between 1.7 and 1.8 start with 1.7. Great. I'm starting to compile the solution. I can go and get, using this method, any number of decimals that I want to, and they will all be exact decimals. So the next one, try a number between 1.7 and 1.75. We got less than, more than, so the interval is in there. Then try 173 to 175. That worked. And then when you try 173 to 174, that will work. I had to abbreviate because class was ending. And then I pinned down the second decimal because all of the numbers in this interval start with 1.73. Guess what's the next step? 1.73 to 1.735. Test both endpoints. Is it in or is it not in? You can pinpoint the next decimal by cutting the interval further. And you can go infinitely far with this. You can go forever because your answer is root 3, which is infinitely many decimals. So this intermediate value theorem, the way it's stated, the way it looks, yeah, not a big deal, right? Clearly, if I pick a value, right, in between these, the value that made it will be in between A and B. The value and the importance of the intermediate value theorem is this back mechanism that allows us to solve equations. And solving equation means being able to build stuff. This is in a core of everything that we have as a species, actually, right? But we just have much cuter ways to compute things rather than sitting there and cranking this forever. right? But those of you who have some dreams of computer science and programming and so on, there are some if-else statements that you can compile and come up with the algorithm that will, get you the first 4 or 5 decimals precision. It's going to be a lot of computation for the computer, but who cares, right? Computers are there to just compute.
So where did you grab that from?
No, this is, I teach also Calculus1 on Saturdays, and I did this example there. So it's in their notes. But again, this is not something that it's on the exam or something like that. So if you're interested, I can give you the calculation. But on your lab, you should have a question which says, give a 1 unit length interval that traps the solution for certain polynomial. So you pick intervals randomly, right? They have to be, I think they say length of 1. So maybe you want to test on 0, 1, make sure that 1 is less than, 1 is larger than on y values. And then if you get both less than or both greater than, the solution is not in there. Then try 1 to 2, 2 to 3, 3 to 4. So eventually you're going to run into situation where f of a is going to be less than 0 while f of b is more than 0, or f of a to be more than 0 and f of b to be less than 0. So you just need them to be opposite, because as I said, you look at this picture here, f of a is less than 0 because it's on the negative y-axis, and f of b is more than 0. And when you have those 2 points, it guarantees that the solution is trapped. If you have both of them larger than 0, right? Let's say the second one is here. So that's your A and that's your B, where clearly both are larger than 0, and the solution is not included in that interval A to B, if it's there. Or if it's here, doesn't matter. Peace.